In this lecture, I'm going to review the main concepts in the topic pressure. These main concepts include concepts such as the definition of pressure and its SI units, factors affecting pressure in solids, application of factors affecting pressure in solids, derivation of equation for pressure in liquids, and then the application of factors affecting pressure in liquids, the YouTube evidence that the atmosphere exerts pressure and measurement of atmospheric pressure, as well as measurement of pressure of a gas. Now, who is the most ideal student for this lecture? In other words, who will benefit most from this type of lecture, which is just a review? The most ideal student for this lecture is the O-level candidate, that student who is just about to sit for a major examination. You may have taken 4 years to study so many topics, and you may have forgotten some of the topics that you learned in the first year. So this review will help you to consolidate these concepts in this particular topic. The other candidate who can benefit from this is the candidate who is just about to sit for an internal examination or a test that involves concepts in pressure. So these two students are the most ideal for this particular lecture. So if you're one of these students, welcome. Now let's go straight to the definition of pressure and its SI unit. Pressure is defined as force exerted normally on unit area. At this point, I want to state that pressure is a derived physical quantity. It is obtained from two other physical quantities which we have covered, which is force and area. So when you divide the force and the area, you get this physical quantity which we call pressure. So it is a derived physical quantity. So the equation which is associated with this definition or stems directly from this definition is this one: pressure is equals to force over area. So you're able to use this equation to calculate pressure if given force and area, or calculate force if given pressure and area, or even calculate area when given pressure and force. This involved the use of the triangle, a concept that I've covered when I dealt with density. So look for the lecture entitled Measurement 1, where I've dealt with density, where I dealt extensively with the use of the triangle. Now, from this equation, we can see that the SI unit of pressure is newtons per meter squared, because the SI unit of force is newtons, SI unit of area is meters squared, and when you divide force and area, in order to get the unit of pressure, you just divide the unit by meters, the newtons by meters squared. This is also called Pascal, PA. In physics, we deal with the definition of physical quantities as well as definition of units. The units which we define are any other unit which is not found in the 7 basic units or base units. If this unit fall outside that category, then it must be defined. Normally, these are units of people, scientists who contributed a lot in the study of that particular concept. Pascal is the name of a person. Newton is the name of a person. Elsewhere, we will define Newton. But at this particular point, we want to define Pascal because it is a unit of measurement of pressure. It is the other unit other than the Newton per meters squared. So when units of physical quantities are names of people, we usually define one unit of that physical quantity. In other words, Pascal is the name of a person. So we want to define 1 Pascal. Just like we will be expected to define the Newton, we'll be expected to define the Coulomb, the Farad, the Volt, and so forth. These are names of people, and when the physical quantity is given the SI unit of the name of a person, then that unit must be defined. So remember, in physics, we deal with the definition of physical quantities as well as definition of units. But before we go to that, let me explain the word normal here. Normal means that the force and the area are perpendicular to each other. They make 90 degrees. That is what the word normal stands for. So remember, when you're defining pressure, you must mention that the force is normal to the area. They make 90 degrees with each other. So let's go straight to the definition of the Pascal, 1 Pascal. From the equation, pressure is equals to force over area, we can say 1 Pascal is equals to 1 Newton over 1 meter squared. Everything 1, 1, 1. And in words, you can say 1 Pascal or the Pascal is the pressure exerted when a force of 1 Newton is applied normally on an area of 1 square meter. At this point, there is the word applied normally. So it is important to add that word there. So it should read 1 Pascal is the pressure exerted when a force of 1 Newton is applied normally on an area of 1 square meter. And that is how we define the Pascal. Now let's look at factors affecting pressure in solids. There are 2 factors, force and area. The first factor is the magnitude of the force. Usually you meet this kind of question in the exam where you're asked to state and explain factors affecting, say, pressure. When you say force, you have stated the factor which affects pressure. When you say that pressure is directly proportional to the force, you are explaining, because you are stating how does that physical quantity depend on this other quantity. When we say that pressure is directly proportional to the force, it's important to appreciate at this point that pressure is the dependent variable while force is the independent. In other words, when we change force, it affects pressure, not the other way around. So if you double the force, the pressure is going to double. If you halve the force, the pressure will be halved. That kind of relationship is referred to as a direct proportionality relationship. So pressure is directly proportional to the force. Number 2, area of contact. At this point, I want to mention it is not surface area. It is the area of contact, because here we are dealing with a physical quantity which depends on 2 objects making contact with each other, touching each other. So that area of contact between the 2 objects is what matters. It is not the surface area. So pressure is inversely proportional to the contact or to the area of contact. What does this mean? If area of contact is doubled, the pressure is going to be halved, and vice versa. Now let's look at some of the applications of pressure in solids. Usually get this question. It is easier to cut with a sharp knife than a blunt one, and then you're asked to explain. That is a fact. It is easier to cut with a sharp knife than a blunt one, and that is why we normally sharpen knives. When you sharpen the knife, you are reducing the area of contact between the edge of the knife and the object which you are cutting. So a sharp knife has a very small area of contact. So a small amount of force will be used to produce a large amount of pressure. So when you use a small amount of force, you don't get as tired as somebody who is using a blunt knife and is expected to use a large amount of force in order to produce the required pressure. Let's look at application number 2. A person who is wearing high-heeled shoes is likely to dent a wooden floor than a person of the same weight wearing flat-soled shoes. Notice that the force that these two people exert on the ground is the same, because the force is equal to the weight of the person. But the area of contact between the person and the ground is different. The one who is wearing high-heeled shoes, the area of contact is very small. And we have seen that when even a small amount of force is exerted to a very small area, then the pressure produced is very high. And that is why that happens. Number two, you have also seen this. Heavy trucks usually have very many tires. Now, why is this? The number of tires increase the area of contact between the truck and the road surface. When that area is increased, it helps to reduce the amount of pressure that this heavy truck is exerting on the road, and therefore the road surface does not wear out quickly. If this one was not done, the road surface is going to wear out very fast, because that heavy truck will exert a large amount of pressure. And you've seen that when the truck offloads, that is, the load is removed, they find it necessary now to retract some of the tires. Some of the tires are pulled up so that they are not making contact with the road. This is done in order to produce the necessary pressure to provide the required grip of the tire on the road surface, so that the vehicle does not slide off the road. If that one is not done, then the vehicle will be very unstable on the road, and it can easily skid at corners, because the tires are not making proper grip. They are not producing proper grip on the road surface. Why is that? The pressure has been significantly reduced by keeping the area the same. So in order to increase the pressure after they offload, because offloading means reducing the weight of the truck. When you reduce the weight of the truck, you have reduced the amount of force that the truck exerts on the road. That is going to reduce the pressure. If it goes beyond a certain point, then that is where that skidding occurs. So the drivers find it necessary, or it is a requirement, that they retract some of the tires so as to reduce the area in order to keep the pressure, in order to retain the correct amount of pressure for proper grip of the tire on the road. Let's look at the fourth example or application of pressure in solids. We know this, that when you are given a block of wood, for example, or rock or stone, you are asked to calculate the maximum pressure it can exert and the minimum pressure. It's important to recognize that a heavy block of stone will exert greatest pressure when resting on its smallest area of contact, and it will exert least pressure when resting on its largest area. Of course, the force exerted is the same in both cases, because it is equal to the weight of that block. And I hope you can remember that weight is equal to mg. Another point I ought to have mentioned when I talked about the definition of pressure here are the units of area. When we say that the area must be in meters squared, sometimes you're given area in centimeters squared or millimeters squared. It is important to know how to convert from centimeters squared into meters squared. And you use the simple conversion unit that 1 meter squared is the same as 10,000 centimeters squared. Or 1 meter squared is the same as 1 million millimeters squared. So that conversion unit is important. When it comes to the mass of the object, like for instance, this block here, you may be given the mass of the object instead of being given the weight. So it is important to know how to calculate the weight of the object when you are given the mass. And it's very simple. weight is equals to mass in kilograms times the value of the gravitational field strength at that point, or W is equal to mg. And of course, don't confuse the G with grams. The G is not the same as grams. The G stands for gravitational field strength. That is the amount of force that the gravitational field exerts on unit mass. On Earth, it's got a value of 10 Newton per kilogram. On the Moon, it is 1.67 Newton per kilogram. On another planet, such as Jupiter, it is 30 Newtons per kilogram, and so forth. But you will be expected to use the value of G, that is gravitational field strength, as 10 Newton per kilogram when you are doing that experiment on Earth. So these are some of the things that I'd like you to observe. Next, we will look at pressure in liquids. Now let us turn to pressure at a point in a liquid, because liquids also do exert pressure. And we are going to start with this equation. Pressure is defined as force divided by area, or force per unit area. So if we look at the bottom of this container here, it's got a liquid up to a depth h. This liquid has got density rho, and the cross-section area at the bottom is A. The amount of force that this liquid exerts on this area is equal to the weight of the liquid. Weight is calculated from mass by multiplying the mass by the gravitational field strength, here, mg. And then mass can be calculated from the density of the liquid and the volume of the liquid. So this m is density of the liquid times the volume of the liquid. Of course, there is G here, and that G also appears there. The volume of the liquid is the volume of this shape, this blue shape here. And it will be given by the cross-section area, which is A times H. So that is how we get the volume of this liquid. So V is A times H. So we've got the weight of the liquid, which is rho A H G, which will give us the force. So in place of this force, we are going to write rho A H G, and then retain this area as given here. So the force is rho A H G divided by A, and once this A cancels out with this A, we get the pressure at the bottom of the container as we get the pressure at the bottom of the container as rho Hg, where rho is the density of that liquid in kilograms per meters cubed. H is the depth of that point from the surface of the liquid. And of course, G is the gravitational field strength. Of course, this is the pressure at that point due to the liquid alone. At the end, we are going to look at how we calculate the actual pressure at that particular point, which also includes pressure due to the atmosphere. Now at this point, we can look at factors affecting pressure at a point in a liquid. And they are here: the density, the depth, and the value of the gravitational field strength. So the first factor is pressure at a point in a liquid is directly proportional to the depth. Again, we know what direct proportionality means. Pressure at the same point is directly proportional to the density. The higher the density, the greater will be the pressure at that particular point if the height is maintained. For instance, over here I've got fresh water, and this is salty water. But salty water has got a slightly higher density than fresh water. So although the two heights are the same, this one and this one, the pressure at the bottom of this container will be different. The pressure for the salty water will be higher than the pressure for the fresh water. if I go back here, when we said that pressure is directly proportional to the depth, the deeper you go into a liquid, the higher will be the pressure. Of course, the third fact, which is usually taken as not a factor if this experiment is being done on Earth where the value of the gravitational field strength is the same, that third factor is the value of the gravitational field strength. If the value of the gravitational field strength changes, as when we move from the equator to the poles, it changes slightly, or when we move from the surface of the Earth to a distance far away from the surface of the Earth where the value of the gravitational field strength is different. So, in that case, G, which is the gravitational field strength, is a factor which affects pressure at a point in a liquid. But when you're asked to state two factors, always state the first two. And then the third one can come in if you're asked to state the three factors. Or if the question is very general as to ask you to state factors affecting pressure at a point in a liquid. The next thing that I want to consider from here is the actual pressure at a point in a liquid. You see this pressure, this surface of the liquid here is subject to atmospheric pressure. So the atmosphere is exerting a force on this surface of the liquid. In fact, it is exerting pressure at this point. So the total pressure at the bottom is equal to atmospheric pressure plus the pressure due to the liquid column. Previously, we have worked out pressure at a point in a liquid as being pressure which is due to the liquid alone. We did not include the atmospheric pressure, but here we can include the atmospheric pressure in order to get the total pressure at the bottom of the container. Now let's look at the specific applications of these concepts.